So we've seen several nice examples now of using undetermined coefficients, making reasonably educated guesses as to what the form of the particular solution ought to be, plugging in and working out the details, finding those undetermined coefficients. Here's an example now where it's not going to work well. So there we go. We look at the right-hand side. That suggests that we ought to try a function of this sort. The problem is that if you take this, plug it into the differential equation, and see what it becomes, what you end up with is 0 equals minus 2e to the x. The entire left-hand side all cancels and becomes 0. Now, how did that happen? I mean, how could it be that everything just canceled? Well, in fact, this equation here is something we've already studied. This is a homogeneous equation, and we know how to find homogeneous solutions. You take the left-hand side and you write down the characteristic polynomial. The characteristic polynomial in this case is p of lambda is lambda squared plus 2 lambda minus 3, and you look for the roots, and it's not hard to confirm that among others, lambda equals 1 is a root of that characteristic polynomial, and that means that this is a homogeneous solution. So, namely, it's a solution to this homogeneous equation. So the reason that it didn't work out in my attempt to make this a particular solution is because it can't be a particular solution. It's a homogeneous solution. So that's the problem. Okay. All right, so what do we try then? What do we do instead? Keep in mind, what we're really interested in, our real strategy, is to put into here, not necessarily exactly whatever's on the right-hand side, but to put into here something so that either it or its derivatives will create terms that can cancel, that can balance with what's on the right. So maybe it's not a term from y that balances the term on the right. Maybe it's a term from y prime. So let's remind ourselves that xe to the x, when you take its derivative, will have a term that's just e to the x, which can therefore have potential to balance with our right-hand side. So let's try some multiple of xe to the x. Put that into our differential equation. Differential equation becomes this. Note that the y prime, gotta do a little bit of algebra to work out what that y prime is, and likewise y double prime are just those things. And conveniently, all of the x terms end up canceling. And that's algebra I'll let y'all work out for yourselves. But the punchline is, after those x terms cancel, you just end up with this. The e to the x is canceled. You solve for a. A ends up being negative 1/2, and you found a solution. Okay. So the moral of this story is, when you're looking for particular solutions, it's not going to have a chance if your guessed particular solution is already known to be a homogeneous solution. And let's say that a little bit differently. Coming back up to here, remember our characteristic polynomial was p of lambda equals lambda squared plus 2 lambda minus 3. Here, this number is 1. That's our r. Right? And said differently, what we need to watch out for is if r is a root of the characteristic polynomial, then we've got a problem. Something's going to go wrong. Okay. Now, here's a theorem that will do some of this guesswork for you and anticipate these situations. We're not going to prove this theorem right now. We will do the broad strokes of a proof a little bit later on when we have some more sophisticated tools to work with. But nevertheless, we're going to start making use of this theorem now, as it will help us very strongly in making good guesses. Okay, so here's what the theorem says. By the way, you'll notice this theorem takes up the entire page. It's a lot to talk about. So let's go slowly and carefully through this theorem. Start with a differential equation. Non-homogeneous. Okay, note constant coefficient linear on the left. Okay. As usual, the left side of the equation we're going to call L of y. That's very, very convenient. And as usual, we're going to call the characteristic polynomial P. Okay. All right. Now let's talk about the right-hand side. The right-hand side is, in this theorem, has to take the following form. Now, not every function takes this form, certainly. So this theorem is not always applicable, but this is very widely applicable. A very broad collection of functions actually take this form. Now, before I get into the details of what we do, how do we find our guess, our particular solution guess, let's look at this form and see how many different versions this can take. Keep in mind there are a lot of constants in here that could be any value that we want them to. So, for example, this a value here, that could be anything. It could be 0, in which case this whole term goes away, and I have only this left. Perfectly fine. This k could be any integer, positive integer. This little a could be any real number. This little b could be any real number. And likewise, this capital V. So there's lots of numbers, lots of variables in here that really it could be lots of different things, and thus this G could take many different forms. So for example, it could be ax to the k. It would be ax to the k if b were 0, making this whole thing 0, and if this little b were 0, then that would make cosine of 0, of course, 1. And if little a were 0, then I would have e to the 0, which is 1. And note that this whole thing then would just be ax to the k. Likewise, with appropriate choices of the various parameters that I have in there, I could make that look like a monomial times e to the ax. I could make it look like something of this sort. In other words, there need not be an exponential term in there. Lots of different variations. Okay. So, again, even though this is not a thoroughly general theorem, this is a widely applicable theorem. Okay. Considers a lot of different right-hand sides. Okay. Now, with all of that said, we've got a left-hand side with a characteristic polynomial. We've got a right-hand side that is of a particular form. Here's our guess. And this is what I like to call the naive guess. This is a good starting point. This, like I say, this is called a naive guess. Now, let me talk about why I call this the naive guess. If you were to just take the naive approach to these problems and say, well, let's think about what I would speculate ought to be in there and what kinds of extra terms show up when you take derivatives, etc., then this is what you end up with. And you can see that just directly. If you take this right-hand side and start taking derivatives, what happens? How many kinds of different terms do you get when you take derivatives of the terms in this right-hand side? Well, when you take a derivative of a product of three things, you're going to be using the product rule. So you'll be effectively, one term at a time, be taking derivatives of the different factors here. When you take derivative of cosine or sine, you get cosine or sine. Nothing new comes up, in other words. When you take derivatives of exponentials, you get the same exponential. A different constant out front, of course, but you get the same form. The only thing it really changes is that when you take a derivative of a monomial, you do still get a monomial, but of degree 1 less. So, exponential times cosine, exponential times sine, all that business stays the same. The only thing it really changes is that these powers of x might become that or lower powers of x. Okay, so with the right-hand side being this is what you would sort of, this would be your starting point. This would be your guess as to what the solution would be. And one of the results of this theorem is that under certain conditions, this will work. This naive guess will be a particular solution, and you just have to work out what those constants are. And let me write down now, just for the for later reference, I'm going to refer to this as the naive guess. Okay. Right. Now, what are the conditions? Under what circumstances will this naive guess work? The conditions, you can actually kind of see it from what we were talking about previously. What went wrong in this last example is the root, the r from the right-hand side was a root of the characteristic polynomial from the left side. Ultimately, that's what it was that made our naive guess actually be a homogeneous solution, and therefore not possibly a particular solution. So this is what we got to watch out for. When the r on the right-hand side is a root of the characteristic polynomial that comes from the left-hand side. So here we go. In this case, the thing that we have to, the condition we have to put in order to make for this to work is that the r determined by the right-hand side, and I'm sweeping a little something under the rug at the moment, the r that's determined by the right-hand side has to not be a root, let me color code better than that, has to not be a root of the characteristic polynomial determined by the left-hand side. Characteristic polynomial determined by the left-hand side. Okay. Now what I swept under the rug here, where did this r come from? There is no r in this expression on the right-hand side. So what do I mean by r? Well, and there's a bunch of algebra that has to be worked out to flesh out the details, but recall that when you have a function of the form e to the a plus bi x, this number here being r, that you get solutions that look like that and that. So this a and this b are, there's a motivation to connect them to this a and this b, namely as the real and imaginary portion of the r that we're actually interested in. There's details to be worked out there, but that's the rough intuition. So that's what this r is. This r is the complex number whose real part is the coefficient in the exponential, and whose imaginary part is the coefficient in the trig, in the sine or cosine. Okay, all right, so what we have then, whatever the right-hand side is of this form this r. Whatever the left-hand side is, form your characteristic polynomial, and then ask the question, is the r a root of the characteristic polynomial? If it is not a root of the characteristic polynomial, then your naive guess will work. Okay, so that's first part of this theorem. Now there is a second part of this theorem, and the second part says, yeah, well, what if it is? What if the r from the right-hand side is a root of the characteristic polynomial? Let's say it's a root of multiplicity m. Right? Is a root. Well, here's the good news. The good news is that even though the naive guess doesn't work anymore, the naive guess is a large part of what actually does work. And specifically, if this is a root of multiplicity m, actually let me do it like that. So if it is a root and if the multiplicity is m, just multiply by x to the m. Multiply your naive guess by x to the m. That will work. Now we definitely do not have the tools to prove this theorem at this point. We will once we get into Chapter 5. We're going to have some very powerful tools develop early in Chapter 5 that will help us prove this result. At least we'll be able to sketch out the proof with a bunch of algebra that we won't slog into. But that's the big idea. Okay. All right, so let's make use of this theorem now. Here we go. Here is a differential equation, non-homogeneous, right? And let's start speculating on what our guess ought to be. Now, according to the theorem, we need to first identify what's the characteristic polynomial and what are the roots. Let's do that first. Here's the characteristic polynomial. In this case, it factors pretty nicely. There you go. And you can see our roots right here. Those are the roots of the characteristic polynomial. Fine. Now, let's look at the right-hand side. The theorem says that we look at the right-hand side. Here it is. And we identify these numbers. The 1 there and the 2 there. And we use those numbers to help us form this number called R. A plus BI. That didn't show it very well. Let me do that in a different... Let me put this 1 there. Yeah, there we go. So that number and that number go together to help us form that number. 1 plus 2i in this case. Okay, so what we have to decide now is the R that comes from the right-hand side, is that a root of the characteristic polynomial that comes from the left-hand side? And in this case, you can see that yes, it is. It is indeed a root of the characteristic polynomial that comes from the left-hand side. Okay, so looking back at the theorem, can't use my naive guess. I have to use this. After all, R is a root of the characteristic polynomial. By the way, it's a root of multiplicity 1. The multiplicity is 1. And so whatever my naive guess would have been, following this naive rule about just speculating about what kinds of terms it looks like it ought to be there, whatever that naive guess would be, I need to multiply by x to the power of that multiplicity, and that multiplicity is 1 in this case. Okay, so writing down the form now. Writing down the form of the guess. Let's start with the naive guess, looking at this right-hand side. That's the right-hand side of our differential equation. We're motivated to write down terms that look like this. Right? Just thinking about how derivatives work. When you take derivatives of cosine of 2x, you're going to get cosine 2x, and you're going to get sine 2x. The derivative of this exponential, well, that's still the same exponential. But when you take derivatives of, I'll use red. When I take derivatives of x, you're going to get terms that look like x, sure, from when you're taking derivatives of other things, but the derivative of x is a constant. So you're going to have the x terms, but you're also going to have these constant terms in here. Okay, again, this is our naive guess. That's not the correct guess that we're going to end up with. R is a root of the characteristic polynomial. It's a root of multiplicity 1, as we just observed. And that's why you multiply all of this by an extra factor of x. Okay, so it's a long and tedious process of figuring out what the right form of the guess is, but it gives us the correct guess. And by the way, here's a rewrite. This is the exact same function. I just sort of distributed the factors of x there, like so. But this is the guess that would work in that differential equation. Now, you could take this and plug it into the differential equation and take the derivatives and collect the terms, etc. I encourage students not to do this one. There turn out to be a very, very large number of terms that show up when you start taking derivatives. In fact, all the way up to the second derivative, don't forget, right, the second derivative here, of this guess, which itself has 4 terms. So this gets out of hand, and it's not a reasonable length practice problem for students to do. So don't do this particular one, no pun intended. The purpose I had in showing you this example was to show you different issues that can come up. Right? I wanted students to see how to deal with a factor of cosine, how to deal with an exponential, how to deal with a power of x, and how to deal with the unfortunate coincidence. Okay. All right, one last thing to talk about. What if you have multiple terms on the right-hand side? So, for example, how would you deal with the right-hand side that looks like this? Well, this function, as written, does not fit our form. It just doesn't. Individually, the 2 terms do. X squared fits our form. Right? E to the x fits our form. We're appropriately and cleverly chosen values of the various parameters. But by itself, all at once, this does not fit our form, and we cannot apply our theorem. Okay. Well, it turns out that you can deal with these terms one at a time, and it's a consequence of this observation here. Now, you'll note that all that's happened here is I've said, well, looking at your right-hand side, what if you were to take those terms one at a time and suppose you found individual particular solutions? And note that all I've done is write down how these, by applying linearity, give me that. This is just an observation of linearity. But the punchline is that if you look at these terms one at a time and find the forms for their particular solutions, second one now, write down the form for its particular solution. If you add those together, what we have is that will be the correct form for the particular solution for these terms together. So, nice easy example is here. Application. So, looking at this term, that motivates these terms in our guess. Looking at this, that motivates this term in our guess. All together then, for the actual differential equation we're interested in, I'm just going to combine these terms, and this is the form that I should try as a particular solution for that differential equation.